Hello, good evening, everyone. How are you all doing? Okay, just a second. Mhm. Okay. Mhm. And then, everyone good? Yeah. Okay, good. Now here today, let me see what we're going to cover today. So we finished projectile 2D motions. Now we're going into the next chapter, so this chapter number 4, Newton's law of motion. Mm, Okay. So if I go to chapter 3, chapter 4, share my screen. Oh, okay. You guys can see my screen, right?
Yes.
Okay, good, good. And then let me this technology. Okay. So now today we'll be talking about like a force and Newton's law of motions. So now, as we said, like up to now, in one-dimension motion and a two-dimension motion, where we did not consider anything about the mass. We only talking about velocity, acceleration, time, distance, displacements, right? So that was the consideration of the kinematic motions. And then we also learned about addition of a vector, how these vectors are added if the vectors are in two-dimension motions. And now from that one, from next on to move on is how what if we include a mass to this kinematic equation? So what does that look like, right? And that brings us to our next topic called force and also the Newton's law of motion. And as we know, already know force. So there, what is defined force? So everyone must know very well from your high school physics and everything. So let me bring my chat. Oh, okay. I need to do the attendance as well. In the meantime, I will also create an attendance for here and attendance code. Let me bring this thing on the side. 5484. Use the code 54884 to check in yourself for the class. Okay. Okay. So now coming back here, force. So from high school force and in anything, right? So what we know, any push or pull, right? So
Okay.
that, yes, Alexander. Okay. So any force of push or pull between the objects and its environment, right? It could be, it does not need to be a human interactions. It could be an object to object, right? Any kind of those interactions is known as a force. So that lets the object to change its uh, position with respect to time, right? And this force and pull has both magnitude. So now again here, so saying the definition, push or pull, right? Push and pull. So what does that mean? Push means you are pushing, you are moving an object away from yourself, pull means you are bringing an object closer to you. So that means here the direction is already involved. So that means force is a quantity, it has a magnitude, and it has a direction as well, right? And so hence, when a physical quantity that has magnitude and a direction is known as a vector quantity. So hence, my force, by definition, it is a vector quantity as well. Okay? And in other words, if we apply a force, then that force will create an object to move. And once that object is moving, so there is a velocity, and that means there is some acceleration, right? So Mariam, so you sign in late. So here's the class check-in code. So use this code to check in yourself for the class. Okay. So in other words, force accelerates an object and changes the direction of motion. So now, even if an object is moving with a constant speed, but it is going in a circular motion, right? So there is an acceleration, and that is due to a force. If there is no force, then object will not change its direction. So that means if the object is moving in a straight path with a uniform motion, so uniform motion that is the velocity is constant. So in that conditions, we will have no force. Why? So that is the condition of a case where the net force is zero. So what does that net force means? So now this brings into conditions when we have like multiple forces acting on an object, right? Suppose you are sitting right now, you are sitting in a chair, right? So you're relaxed, right? So you are not pushing, you are not pulling. So does that mean there is no force involved? Of course, there is a force involved. You are pressing against the ground and ground is pressing against you. But that force, that is you pressing against the ground and ground pressing against you, so those two forces are equal and opposite. So they cancel each other, right? And that is called net force equals to zero. Okay. So that's one here. If multiple force act on an object, then it accelerates to the direction of net force only if the net force acting on the object is not equal to zero. So now, if the net force is not zero, then it will accelerate. So that means the velocity will keep on changing with respect to time. That's what it means by accelerate, right? So like if you hit a gas in a car, so it accelerates, right? Because the net force is not there. But now when the car is like uh, in a parking lot, sitting just there, so there's a net force equals to zero. The car weight is pressing against the ground and ground is giving a uh, reaction force to the car. Okay. So now, since we talked about the force now, until now, we gave an example of the force that are contact force, right? So where you need to have a physical contact. So now there are different type of force where it does not need a contact as well. So one of the force that we just talked is a contact force. So meaning to apply a force, we need a physical contact. Like for an example, like pushing away the uh, couch, pulling your luggage in the airport, pulling a string, kicking a ball, or like during construction, you are moving like an object from one place to another. So those forces all need a physical contact. And another type of force is called non-contact force or a field force, right? So what does the non-contact force means? So where there is no physical contact. An example of those are electromagnetic fields, right? Electric fields. So those forces does not need any physical contact. So there is a reaction between the fields. Okay, so now let me go here. Make sense until now? And what's the example of this non-contact force? So we've been talking about this several times in our topics. So that is called gravitational force, one of the example, right? Where gravity is pulling against an object towards the ground, right? And then this object is being accelerated towards the ground with the acceleration that is equals to what? Z, the value Z. Make sense? Make sense? Where G is the acceleration due to gravity, and then so that is causing a force. And another type of like a contact force is also like a friction force is a contact force, right? And non-contact force are like another is like a magnetic force. So those are all different type of force. Now, so like here, and the force between the Earth and the Moon, the planets. So these are all gravitational force, and the other non-contact force, right? Now, since we said, okay, when there's a push and pull, and we talked about the net force, right? So now, based on that one, so there is a law for the force, which is called Newton's law of motion, right? So what does the Newton's law of motion mean? So it has three different laws of motion. First law of motion, second law of motion, and a third law of motion. Okay. So first law of motion, what does it says? It says the object will continue to be in the state of rest. Again, from our first chapter, what we know, there is no absolute rest. It's just based on the frame of reference where you're looking at, right? If you are in an airplane, inside the airplane, you are in a chair, like you are in your seat, you are not moving, right? But people in the ground see the whole airplane is moving, so that means you are moving it itself too. So that's why absolute rest or absolute motion is not really uh, possible. But now, according to Newton's first law of motion, is like an object continues to be in the state of rest or in the state of uniform motion. So what does the uniform motion mean? So uniform motion mean the motion that does not change, that does not accelerate. So the speed does not increase or decrease, right? It stays in a uniform motion in a straight line. So in a straight line means, so its direction also does not change, right? So now, if we want to change the state of its rest or the state of uniform motion in a straight line, we need to apply an external force. But if there is no presence of external force, then it will continue to be in the state of rest or a state of uniform motion in a straight line. Make sense? Right? Pretty much simple. Newton's first law of motion, we only know. So now again, as I told you, so initial frame of reference. So again, so this is also depend on the frame of reference from what point of view you you are looking at it. So if you are driving a car, the passenger sitting next to you in a car is in rest. So they are, so they might be sleeping, they might be like uh, talking in a cell phone, but they are not moving with respect to car. They are not moving forward or they are not moving backwards. So they are moving along with the car. So that means in that frame of reference of a car, you and the passenger in the car are in the rest. But now if you look outside the window, what do you see? All objects are moving backwards, right? So, and then according to Newton's first law of motion, so an object does not accelerate unless acted by an external force, right? And this is valid only in inertial frame of reference, right? So what does that mean? If the frame of reference itself is not accelerating. So what is the definition of inertial frame? If the frame of reference that is not accelerating, if that frame of reference is moving with a constant velocity, constant speed, then that frame of reference is also inertial frame of reference, right? So meaning any frame of reference that moves with a constant velocity related to an inertial frame. So suppose you found an inertial frame of reference, right? And then, so there are multiple aspects of looking at the object, right? So now if any other person in any other frame of reference will be also called to be in an inertial frame of reference if his or her frame of reference is not accelerating, is moving with a constant velocity relative to the your frame of reference. And both of these frame of reference is called inertial frame of reference. Make sense? Example, right? If you are starting your car from a stop, like in a ramp, right? So you are going like from ramp 35 miles per hour and you are going to like what, almost like 60, 65, 70, right? Within that time of frame. And that time of frame is not an inertial frame of reference because now at that point you are accelerating. Make sense? Right? But again, if you are going with the same speed, but again you are changing your direction, then also it is not an inertial frame of reference. Right? So for inertial frame of reference, the velocity should be constant. Okay? Like for an example, so I have these coordinates x, y, and z, so which is like say like frame reference A. So you are sitting in this one, and we have another frame of reference, right? So coordinates. So the trees, this house, and everything, so is based on the second frame of reference B, and where the velocity is 0. So that means this frame of reference is at rest with respect to this frame of reference. So that means this frame of reference is also inertial frame of reference. Okay, but now this frame of reference, while being 0, but it can also move in one direction with a constant velocity. So now in this condition, if it is moving with a constant velocity, then this is still a inertial frame of reference. Okay, only thing is it needs to have a constant velocity. Make sense? Right? So what are non-inertial frame of references? Right? For an example, so suppose you went, so you are going in the morning for to your work, and you had a coffee, and you put a coffee cup on top of the car, right? And then you forget and you start driving away. So now if you drive, your car will accelerate towards the right. So now what happens to the cup? So cup will have like a equal and opposite acceleration in the opposite direction, meaning cup will fall off. So this is a non-inertial frame of reference where the car is who is accelerating. And at the same time, for somehow, so you drove with like a constant velocity, and then you had a cup of a coffee still on top of your car, and now all of a sudden when you stop, right? So in case of deceleration, so this cup will fall forward while your car is here. So and during this period of time where there's accelerating and decelerating, and those are the times when it is a non-inertial frame of reference, or you are changing your direction, or you are turning around the car. So those are all non-inertial frame of reference. Okay, makes sense? Okay, everyone is getting it. Very good. And frame of reference where the first law of motion does not hold, such as accelerating and deaccelerating, frame are called non-inertial frame of reference. So meaning this first law of the Newton's first law of motion fails in a non-inertial frame of reference. Because in a non-inertial frame of reference, what did we say? Sorry, in a first law of motion, what did we say? We say the object will be in a state of rest or in a motion unless acted upon by an external force. So when in the first case there was a car, there was a cup, right? And the car accelerated. What happened to the cup? So cup was initially at rest. So cup accelerated in the backward direction. It did not stay in the rest. But now here, the car in the second case, deceleration. So before it stopped the car, so car was going in a constant velocity, right? So in that conditions, it was an inertial frame of reference. And Newton's first law of motion was valid because both the car and both this coffee cup was in a state of constant velocity. But now as soon as the car stopped, what happened to the car? It was not in the state of rest, but the car was in the rest. Car came to the rest, but the cup did not come into the rest, right? And during that period of time, the Newton's first law of motion does not hold. Correct.
When you refer to it being an inertial or non-inertial, like in this case, do you mean like the driver or the observer?
Uh, so like this cup has its own frame of reference, right? So now in the car, so like from again the driver is also right. So because now you are accelerating, right? You are changing your position with respect to time, right? That's why when there's like a uh, when someone hits like a brake in a car, right? So what happens? You tend to go forward, right? Because at that point, so big when the car was going with a constant speed, you were sitting in a chair with no problem. So you both your car and you both were in the same frame of reference. With both of you were in the rest, or like you felt to be in the rest, the seat of the car, right? Or like no, not the rest, but they were going in the same with a constant velocity. But now, as soon as you hit the brake, what happened? So now you are in the different frame, which is not a inertial frame of reference. Because now here it is there is acceleration involved, which is deaccelerating. So that conditions is a non-inertial frame of reference.
Okay.
Okay.
Professor, so I'm trying to understand this from the standpoint of like being on Earth. So if we're on Earth, we're at the same uh, velocity. Would Earth be considered an inertial uh, frame of reference if we're on Earth?
Uh-huh.
But if we're out in space, it would no longer be because it's got motion away from us.
So that's why I said like in the very beginning. So there is no possibility of having an absolute rest or absolute motion, right?
Yeah.
Because the Earth itself is in motion, right? So
Mhm.
that's why like you know we really don't know. So there is no absolute. So now again, if you move out of the Earth, like move really really far, then you might see the Earth is accelerating as well. But now we are such a tiny speck in Earth itself. We don't realize that one. So we see everything around us is not accelerating.
Okay.
Okay. And now, as we said, this tendency of an object to be in the state of rest or in the state of uniform speed in a straight line is known as inertia. So meaning you do not want to change your state of motion either in a rest. If you are in a rest, you don't want to get up and walk. And if you are walking, you don't want to stop. Seems weird, but in generally, if the object is in like uniform motion, if there is no any external force, right? So like for an example, if you slide an object on ice, where there's almost like no friction, right? So it will keep on going, right, out to certain distance. But there are like a very small amount of friction force, so that's why at certain point it will go and stop, or it will keep on going. But the same condition, if you try to slide an object on a table or on a ground, it does not even move, right? So like maybe it slide a little bit further, but it stops. And now this tendency, if there is no any external force, the tendency of an object to be in a state of rest or uniform speed at a straight line is known as inertia. And Newton's first law of motion also says the same thing. Object in a state of rest or in a motion in a straight line, uniform motion, it will continue to be in that state unless acted by an external force. And here the law of inertia also says the same thing. But now why we need to involve this law of inertia? What does this mean? Right? So meaning, so because remember, uh, earlier I mentioned, so there was we studied about the units and then we studied about the kinematics. And in kinematics, we only were interested on the very simplified version of the physics where velocity, acceleration, displacement, time, and was only considered. So we did not need to know or that particular equation of motion does not care if it was a big truck or a small car moving with a certain velocity, right? It did not really matter. But now, in Newton's law of motion, in this chapter, we are involving a mass. So meaning here, what does that mean? Is like larger the mass, larger its tendency to stay in its state. If it's in a rest, it does not want to move. Meaning, if you want to push a book, right? It's easier to push a book compared to if you want to push a car, right? Because the car has a larger mass. So the car has a larger inertia. So that means it does not want to change its state of rest, right? And when the car is in motion, when you hit the brake, it does not stop right away. It travels a very long distance before it comes into the complete stop. Compared to the motorbike or compared to the bicycle, it will stop a lot faster. Why? So now there is a mass involved. Larger the mass, larger the inertia. So larger, it will try to maintain its state of rest or uniform motion. Make sense? And here, when you said like we are hitting the brakes, so we are creating a friction force and all those things, right? Uh, so that what is creating it to stop. So larger the mass, larger the resistance to change its opposite motion, right? Like an example in this one, I have like a ball on a table and a refrigerator. So to push a ball, it is much more easier compared to the push a refrigerator, right? So now Newton's first law of motion gives us a vague idea about the mass, right? It gives you, oh, okay. Until now in the kinematics, we learned about velocity, acceleration, time, and displacement. We never considered about the mass. So now Newton's first law of motion gives you uh, a little bit idea about the mass. Oh, mass does have something to do with it. So meaning larger the mass, harder to move. Smaller the mass, easier to move. So that means mass also involves some resistance. And now because of that, now we want to see, okay, so we apply a larger amount of force to move a larger amount of object, right? So if I want to accelerate some object, a larger object compared to the smaller object, it is much more easier to accelerate the smaller object than the larger object. And now to find this relation between this acceleration and the force, that gives us uh, the Newton's second law of motion. So what the Newton's second law of motion says? The acceleration that has been created due to the force, right? This acceleration is directly proportional to the net force acting on it. And so meaning if I apply a large amount of force, I will create a larger acceleration. But again, that is not always true. Now here comes in the role of a mass, right? But if the mass is like really, really large, acceleration will go down. So that means my acceleration will be inversely proportional to the mass, right? So if my action, if my force is really large and mass is also really large, I'm not gonna get like a larger acceleration. So if I have a smaller mass, then applying the same amount of force, I'll get a larger amount of acceleration. So again, this force is what force? This here is summation sign. You guys, I believe you guys understand this sign, which is capital sigma, right? So this is a Greek letter, sigma, right? That means it's a sum. It implies it is a sum, okay? So sum of the all forces, which is known as a net force. This acceleration is directly proportional to the net force and inversely proportional to mass. And that gives us to a relation where the net force applied on an object is equals to mass times acceleration. Why we need a net force? For an example, if an object is sitting on a table, right? So like here, my phone is in my hand, right? Okay, here. And if I want to push, right? So in these conditions, I'm not pushing, but I'm holding it in my hand, right? And in this condition, the cell phone is not moving at all. So that means in these conditions, the force due to cell phone is acting on my hand and my hand is pushing against the cell phone. At this particular case, the both force, they are canceling each other. and hence the net force is 0. But now if I push my force in horizontal direction, then it is moving forward, right? So now this force on this horizontal direction is greater than the force that is coming through the surrounding on that directions. So that means my net force is equals to mass times acceleration. Okay, it's a net force, not all the force, it's a net force. So where net force is the addition of the all forces acting on it. So in that condition, you have to consider the gravitational force on the ground and the force due to your hand onto the object. And here's an example with the drawing. So this pushing this basketball or mass m1 with the same amount of force will accelerate a larger magnitude. But if you want to use the same amount of force to push this SUV car, it will move a lot smaller distance or it will accelerate a lot smaller. All right. And now for this thing to happen, so now comes the system. So now in these conditions, this Newton's second law of motion is only valid in a uh, two object system. Meaning, so this person is outside of this SUV car. This SUV is one system, this person is another system. Same thing, a ball is one system, this person is another system, right? What does that mean? What I'm trying to say here is like, if you are sitting in a chair and if you pull your legs up from the ground and like sit all your body on the chair, then it is not, you cannot move the chair. But now when you have to move a chair, what you're gonna do? You're gonna put your feet on the ground and then push it against the ground, and then you're gonna move the chair. So in these conditions, the chair is one system and you and the ground is another system. Where that force come from? From the ground to push the chair. Okay? Do you understand what I'm saying? Okay. All right. So, and the unit of force is basically what? Force is like mass times acceleration, and we know acceleration is meter per second square, and mass is kilogram. So the unit for force is Newton, which is 1 kilogram meter per second square. Okay, and this is an SI unit. So whenever you do a problem, these are all in a SI unit system. Okay. So okay, so just a second, I'm gonna show you guys a one demo. Let me bring my demonstration. Get my cell phone camera so that I can show you. And what? Where is? Can you see my what? Okay. on, and so let me get rid of this background. This background effect. Where is it? None. Okay. Right. So now here, you guys can see this one, right?
Yes.
The fan and a cart system. Okay. Let me put a little bit back here. And then, so this is a fan and a cart. So if I will turn this fan, right, with a battery, so it will blow some air, right? So meaning it is pushing air. And then if I will, and this is like almost like a friction free wheels, but not like 100% friction free, but still, right? So now here it is in a rest, right? So now if I will turn on this fan, now what do you think, like you guys, this happens to this cart, fan cart? Need to, so this is mirrored, so like it's like I'm having a hard time adjusting. Just a second, because it's mirrored and I was having, okay, so turn the mirror, turn the mirror. Yes. Oh, yeah. Okay. Right. So now if I will turn this fan on, what happens is that this card battery is not enough. Let me see. And it should be in a level surface, and I'm not sure how level. Second. I put a $2 battery. So now, right? So this card is moving, right? Why this card is moving? Because there is a force, right, towards the surrounding, and then that is moving this card in the forward directions. Now, if I will put this power plexiglass, I will put this plexiglass right here. Okay. Now I'm putting this plexiglass, right, in this one, right? So now if I will turn this thing on, what happens? What do you think will happen? Anyone?
I'm gonna guess that it's not gonna move
Yeah, why?
because there's no airflow.
How it is being blocked? So can you explain in terms of a Newton cycle of motion?
The ability for the force to actually be applied is taken away because there's no, I guess there's no air particles that are moving. So
Yeah. Earlier, when there was no plexiglass, right? So it was applying a force. Now let's see. Okay, let's see here. So basically, virtually it's not moving because the vibration is moving forward. Because the vibration, it's like basically not moving, right? So now compared to this one, if I will take this plexiglass out, back, right? So now what happened? So in these first conditions, so it is applying a force to the surrounding air. So that's why it is able to move. But now when I put this plexiglass in here, what it is doing is it is applying a force to itself. Then now this plexiglass, this air, and this cart is a same system. It is not a two different system, right? The force is acting to itself. And then it is not able to move. And this is an example of like if you have like a gas cylinder, right? And there are like a lot of gas molecules hitting the gas cylinder, but the gas cylinder doesn't move like a propane gas, right? In a propane gas, you have a propane. But now if you connect it in a tube and then release the air or like high pressure, not the I don't want to like release the air, but high pressure gas. And then if you blow it out like in a leaf blower, right? So what happens? The leaf will blow away. But the same air molecule inside the propane is not able to move the propane gas itself because that force is acting to itself within the system. So same thing like you are in your chair right now and with your legs up in the chair and you try to move, you cannot. Maybe you have to like jump really, really hard or something like that to disturb, then only. But in general, not. But now if you want to move it really, what you have to put your legs onto the ground and then push it. Now there is a two different system involved. Like here, it's like one system. This force is acting on the system of the car itself, right? So this air wants to move in this direction, but this cart is pushing in this direction. Air is pushing in this direction. So the force does not move because it's in the same system. So now for this Newton's second law of motion, it needs to be a two different system. Make sense? Make sense, guys? To turn up. Yeah. Mirror and then background and then yeah. Okay. So that means if you see any problem in your physics, so that what do you need to know when you're like looking at Newton's second law of motion problem? You need to see if it's like a two body system or not. If not, then Newton's second law of motion does not apply to that one. Okay, so you're acting a force within yourself, so it doesn't do anything. Okay, we pull this thing away, right? And the next term, so since now we have an idea about the mass, and now we have the idea about the force, right? So now what we're doing is like larger the mass, larger is the inertia. So now force. Now what is this mass and what is this force? And now whenever we say if the same mass is being pulled towards the earth, that mass times the pulling is known as the weight. So that means the central acceleration due to gravity is pulling that object into the ground, right? So now mass is what? It's a physical quantity that also determines the inertia, that measures the inertia of a system, and it's a scalar quantity. So no matter where you go, even if you go to the Mars or if you go to uh, moon, the quantity mass will not change. The thing that will, so that means it is scalar quantity, and only thing that changes is the weight. And also from Newton's second law of motion, what we know, force equals to mass times acceleration, net force. Now, if we take the ratio, in this case, what we're doing here, so this first net force, F1 net, equals to M1 times A1, and F2 net equals to M2 times A2, right? So now, if we apply a same amount of force to two different amount of masses, if the mass M1 and M2, if this F1 and F2, they are equal, so in that conditions, what happens if F1 net equals to F2 net, right? So if we are like in a basketball and also an SUV, if we are applying the same amount of force, so that means this product M1 times A1 will be equals to M2 times A2, right? So now if we do a little bit of algebra, then we will get into the situation where the ratio of mass of the first object over the ratio of the second object will be equal to the ratio of the acceleration of the second object over the ratio of the acceleration over the first object. So m1 over m2 will be equals to a2 over a1. Make sense? So now, if the mass of an object is given, and if the acceleration of the object is given, the mass of the two objects is given, and only the acceleration of the first object is given, then you can find the acceleration of the second mass if this force is applied. So we really, by knowing this ratio, we can always calculate what will be the acceleration for the second object. So we really don't need to know exact value of the force. If we know if the two forces are equal, so here we don't really need to know what is the value of this net force. We just need to know, oh, if I'm applying the equal amount of force, so that means this is true. So that means I can find what will be the acceleration for the car or for the ball. Like in first case, we have a basketball and we have a SUV car. And if we know the mass ratio, and if I apply the same amount of force to the basketball, the acceleration is really high. So that means I can calculate the acceleration of my SUV. Okay? Makes sense? What do I mean here? If there's a basketball and there's a car, and I'm applying same amount of force, F, and also to the car, F, right? And we know the mass of this basketball is m1, and we know the mass of this car is m2. Now, if I apply this amount of force, then this basketball, this, let's say 1 kilogram, and say like 1 ton, right? So that if I know that my acceleration for this one would be 10 meter per second square. So now what will be the acceleration for this car, right? Acceleration for this car if I apply the same amount of force. Then I know m1 over m2 equals acceleration of a car over 10 meter per second square. So by doing this one, so since I know this ratio of m1 over m2, now I will know what will be my acceleration. Now 10 kilogram divided by 1 ton is like 1,000 kilogram, right? Or like 1 ton is like 100, right? So that means, this acceleration will be a lot smaller. Make sense? Right? So here I don't need to know what is the amount of force that I apply to the ball or I apply to the car. If I just know those two forces are equal. Okay? Make sense? Yes, no, maybe. Okay. So, and then weight is like what is the gravitational pull. So the weight of an object is not same as the mass of an object. Okay? Weight is a force, it's a measure of force, right? So it is mass times acceleration, okay? And which is a force, right? So now, then you might say, okay, we measure our weight in a scale and it will give us like maybe like 150 pounds, 180 pounds, right? How did we get that? So that instrument is already calibrated based on this acceleration due to gravity. So it is taking that amount of force and dividing the value by acceleration due to gravity, and it is giving you the mass. So now, if you measure your mass like the way you measure your mass here in Earth using a weighing scale, the digital weighing scale, then if you go to the Mars, you will weigh yourself 1/6 time less because there the acceleration due to gravity is different. That scale is calibrated to measure the weight here in the Earth, mass in the Earth, right? Because the G value is different, so you will have a different value. So that means if you know, because that means the force, weight means a force. So that means force pull in the moon or Mars is different than the force pull on a Earth because weight is a force. And since weight is a force, so weight is also a vector quantity. Make sense? So now here, this weight is written as negative mass times gravity. Why negative? Because it is pulling towards the ground, towards the center of the earth, right? From the surface inward. It is not pulling software. Not from the surface outward, it is from surface to the inward. Okay. And now comes the Newton's third law of motion. Newton's third law of motion and the demonstration I showed you earlier. So that is like almost like the same thing. So what it's saying is like action has equal and every action has equal and opposite reaction. So meaning if there are like two objects, right? And then if you come and collide, so there will be a forces. Now again, you need to know this subscript. What does this subscript means? This is force on object 2 due to 1. F2 force on object 2 due to 1. So this is like a uh, uh, cause, and this is like a the source 1, right? So force on F2 due to 1, and this is force on 1 due to 2. So now when they collide, no matter the size, large or small, or like this, one could be like smaller mass and two could be like a larger mass. It does not matter. The force in that particular condition will be the same. Meaning while you're driving a car, you see a lot of bugs during the night. When you're driving, a lot of the bugs hit your windshield, right? So now the force that car is hitting the bug is same as the force. That force will be same as you see from the bug side, bug hitting the car. So those forces will be equal, but in opposite direction. So like a small rock chip coming and hitting your car, the force that will be the same amount of force your car is hitting the rock chip, and that force will be same as rock chip, rock, like small rock hitting your windshield, right? So those are equal and opposite. So that's what it means here, Newton's third law of motion. So every action has equal and opposite reaction. So now because of this, they move away, right? So now this F21 is equals to negative F12. So force on 2 due to 1 is equals to the negative of force on 1 due to object 2. Make sense? So here negative sign means they are equal and opposite. So they are in opposite directions, right? And same thing here in a swimmer, like here in this case swimmer. So swimmer is pushing against the wall. As C is pushing against the wall, but the wall does not move. So what moves? C moves forward and C gets that acceleration. Okay, so in that condition also there's an action where this lady is creating an action which is pushing against the wall, and the reaction is wall is giving a reaction, and that's how she's able to streamline forward direction. Okay, so your action is this and reaction is in these four directions. Okay, and this is the system of interest. All right, so this is the system of interest, and there's another system here. So this system of interest is applying a force in the outer system, right? So there's a two different system here. Make sense? Because they can detach itself from each other. If they were attached, then yes, it was the same. It was not a two system, but there are two different systems. Make sense until here? Right? Okay. So now, so there's a next topic of same force. Again, so remember, force is a vector, and this force applies the same rule of addition and subtraction of a vector. Okay, so the way we did like last time, the addition of two vectors, right? So like let me go here. Right. So where the vector, when did I do this? We did the vector addition, right? Yeah. So we did this vector addition, right? So x component, y component. So these vector additions. Now force is also a vector. So force will also apply the same thing. So meaning, let me get this one. Copy from this. Paste. Pasting it. Okay. So meaning here, right? So as you see in this particular diagram, so this person is pulling with a string in these directions, but this object is moving in these directions. So this force is the direction of the force that has been applied, but this is the direction at which this object will be moving. And then this, there is a force which is acting away from the surface. Okay, so let me see another very good example. Try. So now in these conditions, so what do you see here? So there's a force, x direction, and this y direction force. But the person is pulling this object at this particular point at with using a string in this direction, right? So there's applying a force F, and that force is making an angle of theta with the ground in the horizontal axis. Now, so this object which is moving in this direction is due to the horizontal component of the force, which is Fx. So this force Fx is responsible for this object to move in a horizontal direction. And now how about Fy? Now Fy is the force which is responsible, the y component of this force, right? So now this Fy is responsible to make your work easy to pull. Okay, why? What do I mean by that? So now if I have an object, okay, suppose if I have an object and in a ground, and now instead of pulling, so now if I will push this object down below, right? So then this time down here, if I will push this thing object down below, so what I can also draw my free body diagram, the diagram of this force. From here, my vector diagram, I can say this is my force which is acting downward, because vector, it doesn't matter this or this, they are the same, right? So now this is acting down below from the ground at an angle of theta. And then the y component of force in these conditions, it is acting vertically downward. So now if I will see this component, so this is my x component of the forces, and this is my y component of the force, right? So now this Fy is acting along the negative y directions, right? So in the I'm pushing this force into negative x directions according to this diagram. So I'm pushing this object in these directions. But now what did I do? So this object, which was already onto the ground under the action of gravity, so I added additional force onto the ground, Fy, right? So now this is going to make our life harder to push an object. So that's why it is much more easier to pull than a push. So like in a lawnmower, right? If your propeller does not work, then it's easier to pull. Like in airport, when you're moving with the luggage, it is easier to pull than to push because of this force component. So because of this component, it makes our life easier, because what did we do? We reduce the amount of force due to gravity acting on this one. We are applying this force on these directions, and which are making this easier to pull, which made our mass looks a little lighter because of this force. But now if you try to push, what we're doing it, you are adding Fy force with respect to, in addition to the force due to gravity, which is acting downward. Okay. And now here you need the component of this force. Now, if you want to find, if I'm applying a force like 10 meter per second, sorry, 10 Newton. If I'm applying a 10 Newton of force in this direction at an angle of 30 degree, what is my x component of force? My x component of force is what? 10 Newton times cos 30 degree. So this is my x component. And what is my y component? So my y component will be 10 Newton times sine 30. Remember here, I did not put any positive or negative because I said this angle is 30. So I'm not measuring this angle. I'm just measuring this angle. So that's why I put it. And now here, when you do that one, so based on this diagram, you should say this force is acting downward and this force is acting in this direction. Okay. So why, how did we get this component? Again, just a refresher. It is based on a right angle triangle. So this is a right angle triangle. So this is my opposite side, this is my adjacent side, and this is my hypotenuse. Okay, make sense? That's why trigonometry will come out very handy if you are so comfortable with this x component and the y component. So that makes it like really easy to understand. X component is always cosine, sine. Again, it depends on which angle. If you are measuring the angle with respect to the horizontal. Okay. So now, until now, we said like, okay, force. But now there's like another term for the force. It's not only the force that you apply, there's the force that some other objects also apply. And they are called some other terms of force called normal force. And there is another force called tension. Are you guys following? Okay. Do you guys need a 5-minute break? No? Yes? Okay.
Okay.
Okay. So now, normal force, right? What is normal force? So what does the name normal means? The normal means perpendicular. But the perpendicular with respect to what? Perpendicular with respect to the surface. Whenever we see a normal force, so normal force is always perpendicular to the surface. It does not matter if the surface is tilted or whatever. So right, if my surface, like in this example, right here, my surface is itself is tilted. My normal force will be perpendicular to this surface in this direction. If my surface is like perfectly horizontal in this condition, like here, if my surface is like this, my normal force will be perpendicular to this direction. And this is called normal. And normal does not mean normal, like literal meaning of normal. So it's okay, right? It's not like okay, normal. It's like normal means perpendicular, okay? So normal force is the force acting perpendicular to the surface, supporting the weight of an object. And it is a reaction force. So like for an example, if I have this object of a mass sitting on top of a table, so then so there is a gravitational force which is acting downward, right? This object, the gravitational force which will try to pull it down. But what is uh, keeping it not going down? So there is a table. Now what this table is providing? This table, this surface is providing a normal force which is against the gravity. And this normal force is the reaction force, which is acting against the gravity. Now, if this normal force is equals to this uh, force due to gravity, so it will stay in an equilibrium state. So it will not move. Okay. So now that gives you situations like in case of like an elevator, right? If you are sitting in an elevator, say elevator, and an elevator is not moving, whatever your weight acting on the elevator downwards and the reaction from the surface, they are equal. Okay, so in that conditions, elevator is stationary and then. But now if the elevator is moving downwards, right? So what does that mean? In other sense, you can also say in a sense that you are pushing the elevator downward. The force that you applied on the elevator is larger, meaning the gravitational force is larger, but the normal force is not enough to keep that elevator stationary. So it is accelerating downwards. So that means in that condition, I will have a less normal reactions. Why? Because I'm moving downward. My gravitational force is larger than this normal force. So now, whenever you are measuring your weight on a scale, a digital scale, what it is measuring is the reaction force, your normal force. How much the surface reacts against you. And that's what it is measuring. So that means if you are sitting in an elevator and you are standing on a weighing scale, right? And if the elevator goes down, you will definitely see yourself showing a less number of like weight or like a pound mass, whatever you call it. It's basically a force. So I would say a weight. Then compared to the case where the elevator is moving upward. If my elevator is moving upward, right? If my elevator is moving upward, in that conditions, my normal force is larger than my gravitational force. So in that condition, you will feel heavy. And that's a kind of a sense, like, so everyone have experienced this one when going into the elevator for the first time. And when it starts moving up, momentarily, when it starts moving up, you will feel heavy, right? And then also like, when you're in elevator, or the momentarily when it starts going down, if you are going from like a higher level of floor to the lower level of floor, so the moment the elevator starts going down, you feel kind of like a weightlessness. And that's what it is. This reaction force in that condition is less compared to the because when it's going down, right? So like suppose you are diving from an airplane, so like a air dive, right? If you do that in that conditions, you are moving down because there is no surface to react to give you a reaction force to keep you stable. So that means in that condition, the gravitational force is much more larger than the normal force or the reaction force provided by the air resistance. So that's why you are still moving downwards. Make sense? Right? Okay. So now there's a rule to draw a free body diagram, and it's called a free body diagram, FRB, or free, sorry, FBD, not FB, FRB. How do it? FBD is like a free body diagram. What does this free body diagram means? So you are getting all the distraction out and you're only considering the body of interest and you're drawing a force diagram on that body. So remember earlier we had a big cube and then we replace that big cube with a smaller dot. So that means at this point, all the mass is concentrated and then we draw this force. Again, in this diagram, I did not get rid of this table, but like generally, this table is also gone out. And then object and here. So now in this condition, this is a force due to gravity and this is normal reactions. And to do a appropriate free body diagram, we will not even draw the table. We'll just show this normal force and the force due to gravity. And also, when we are making a free body diagram, you are only going to draw the forces acting on that object. You are not drawing any forces that is acted by an object. Only forces that is acting on that particular object of your interest. So in this condition, this block, so now which you consider as a single dot, and we will draw all the forces that is acting on this block. And we are not going to draw any forces that block is exerting on anything. But here, F due to G is the force due to gravity, which is acting on this block. And this normal force is the force acted by the surface, table surface on this block. So that's a free body diagram. Make sense? And now, so as we drew here in a free body diagram, right? So there's a force acting on it in a different directions, like, so there's a force. And now here is the next one is a tension. What is a tension? Tension is a force when we are using any medium to pull an object. So meaning a rope or a string, right? A connector. So if we pull an object using that string, so whatever the amount of force that we're applying, that tension is developed in that string. So tension is the force that is developed in the string. Okay. And the direction of the force is always along the length of the string. Okay. If I am suspending an object along the string, my tension will be always along the string, meaning like in most of the case, not here in Texas, but if you go to other different states, there will be a traffic light hanging on a string, right? There's a traffic light hanging on a string, right? So in these conditions, like these are like some poles here, so connected. So in this case, the force is, the tension is the force that is acting on this string here. So no matter what, there is always a force along the string. Okay, and that is called tension. Tension does not mean like a physical mental tension. It's a tension is the tension in the string, right? How much in the force is there? And like, the human also say like, oh, I have like a lot of tension. So like what that means is like you have a lot of job duty to do, and then you are so much pressurized, and you are feeling a pressure, you are feeling a force. So tension is like it's the same exact spelling, tension, and here it's a force that's applying along the string. Okay. Any questions until now? And this tension is represented by letter T. Any questions until now?
No.
Okay. Okay. And like here, I just said like I drew a diagram. Okay, I didn't. So here there's a tension. So like whenever we have this traffic light, so we have this tension T1, T2, and T3. From this point of the knot, at this point of the knot, that there are the three different tension that is acting at this particular point because of this traffic light, which is hanging solely due to the action of gravity. So at this particular point, there are like three tension. This tension 1, tension 2, and tension 3, right? And then these tensions are making an angle theta 1 and theta 2. Remember, these angles are not equal. Why? Because the length of the string in this direction and the length of this string on this side is not equal. So what does that mean? So this tension T1 is not equal to tension T2. Okay? So because this angle. And now how, if I want to find what is my tension T1 and T2, so what I can always do, or like make a right angle triangle and then try to solve it. So now based on this one, the net tension, if this is in stationary conditions, so there's a force which is acted by due to this string, which will be acting in the upward direction, and this invisible force that you see here will be acting against the force due to gravity, which is acting downwards. So this invisible force that is created due to this particular T1 and T2 which is in upward direction, is what is holding this traffic light in a place. So meaning now if I have to draw this in a component form, so this for this one, this for T2. So now in these conditions, T1 will be this, and now T2, the T1x, and this is T2x, right? But now these two components of this tension will cancel each other. So that's why this traffic light does not move left or right, because they are equal and opposite. But now if we look at the y component, so this is my T1y, and then again I will have like same in up direction T2y. So now this both the tension, because the tension due to the string T1 and due to the string T2, so they both are acting upward direction, so they add up, and this summation of this tension will balance the force that is acting downward due to gravity. So T1 plus T2 will be equals to T3 plus mg, right? Okay. So that means now here, oh, so now again, when you draw a free body diagram, what did we do here? So we consider everything, this knot at the point where the force is being acted. I just draw a dot here, and then from here T1 and then T2. So now this angle theta 1. So this angle is also theta 1. From what? From geometry. So these are parallel lines. So that means what kind of angle are they? So this angle and this angle, what kind of angle is called? Do you know the name for that angle? Do you guys remember, anyone? Anyone? Yes, no, maybe.
Is it coterminal?
Sorry?
Are they coterminal or complementary angles?
No, not a complementary. It's called alternate angle.
Oh, okay.
So because this is my parallel lines, right? And this is my transverse line, right? Oh my goodness. What happened? What did I do? Yeah. Uh, yeah. So this is my transverse line, right? And now this angle and this angle are corresponding angle. Angle and this angle. So okay, this angle and this angle is my alternate angle. Alternate meaning, so it is alternating on the both side of the transverse line. This is my transverse line. So alternate side of the transverse line. They are called alternate angle, corresponding angle. So this angle and this angle, because this is a parallel line, and this is also a parallel line. Same thing. So this angle and this angle are equal, corresponding. So they correspond the same thing, but this here, they correspond the alternate side. So that's why, so in these conditions, so when we have this angle theta 1 here, so this angle is theta 1, this angle is theta 2, so this angle is theta 2. So that's why here I can write down this as a theta 1. I can write this one as a theta 1 and this as a theta 2. Okay, make sense? You will need to know this geometry very often, just like that, so that it will be easy for you to draw the force diagram and the trigonometry. So that's why I'm saying pre-calculus is required for this class, because there's a trigonometry involved, there's a geometry involved. And that's one of the prerequisite. Okay. So, but again, so some of you might have taken this a little bit earlier. So I'm just giving you a little bit of refresher every time. Okay. And now there's a rules to draw a free body diagram. Now here, so there's a lady here and they are doing ice skating, right? And so like two other ladies are pushing her from behind and from the left side. So now if I can draw this free body diagram in multiple different ways. So now if this lady is pushing her in upward direction and this lady is pushing her in a right direction, what will be the resultant direction of this lady moving? So it will be diagonal to the right in this direction. So net force will be this direction. So now my F1, which is in this direction, my F2, which is in this direction. Now do the vector additions. First vector, this vector and this vector, they are same, and this vector and this vector, they are same. So that means first vector and second vector starts from the final position of the first vector. So it goes here. So that means your resultant force will be starting for the initial point of the first vector, ending at the final point of the second vector. So this is my resultant force. By the way, did you guys use the GeoGebra app for your vector addition subtraction? Did you play with that? Was it helpful? Helpful? Anyone use that one?
Yeah,
Or
extremely helpful.
okay, good. And now same thing, I can draw here in this format here. So this F1. Now again, I replace this object and this person as a one single dot, because when you draw a free body diagram, we are not going to draw uh, each and everything. We'll just consider everything as a one point. So now there's a force acting on this direction and force acting there. And now here we only represent what is the force. We don't see the cause. We don't look at the effect. We are free in a free body diagram. We just say the source. We just see the like a force acting on it and at on what object, and we'll only consider that particular object, force of acting on that particular object. So now here this person is going to convert into a dot here, this F1 and F2, and to draw this one I can also do, I can replace this vector F2, move it up here, and I get this resultant force vector. And again, this force vector and this force vector, they are the same, so it doesn't really matter how you draw it, right? So you start from here and go there, or you put the object of interest here. And third one you can draw is like, so you move F1 here, you move F2 here, and then the diagonal of this square or the rectangle is the resultant force. Okay, so this is how you draw the free body diagram. So what is that? So now if you look at this one, this is the same as this diagram here. Okay, so this is F1, this is F2. Now this is parallel and equal to this one. This is F1, this is F2. This is F1, this is F1, right? So same thing we can do in a multiple different way. And now, so that was the free body diagram in a plane, right? So now we have to draw a free body diagram in an inclined plane. So if the plane is not flat, but it has a slope. So like for in case of like for an example, in this case, say perfectly very flat, you know, very flat inclined plane, ice hill or a snow hill, and this person is skiing on these directions, right? Remember, we said there is a force due to gravity. Now, what will be the direction of the force due to gravity in these conditions? The force due to gravity is always vertically downward towards the center of the earth. Now, again, this little hill compared to this big earth, this little bit hill could be like this small speck. It's like of nothing, right? So that means, and everything that is acting on this object, the force due to gravity is always acting toward the center of the earth, which is vertically downward. Okay. Now if I see, so now this is my weight, which is acting vertically downward again. Now again, for the reference, I'm keeping this diagram here, but again, I don't need to make this diagram here, put this object here, okay, in a real free body diagram. So now here I'm taking this point of contact or the center of mass, I can take here object. So it really doesn't matter. So now there's a force due to gravity which is acting vertically downward. And then if this is a surface and perpendicular to that one is a perpendicular component of this weight to this surface. And if this gravitational force which is acting vertically downward is making an angle theta with the perpendicular component of this weight vector. So now to counterbalance this W perpendicular, so there is a force which is opposite direction, and this force is what? This is normal to this surface, meaning this N, the normal force, is perpendicular to this surface. Okay. And now the parallel component of this weight is which is acting on this direction, which is along the surface of the hill, right? The inclined plane. So now this is called W perpendicular. This is called W parallel. Right? And now if there is some friction force, so meaning if these are not ice, if there is some friction force will be always opposite to the direction of the motion. Okay. So that means if I have to draw a free body diagram of any object, right, in an inclined plane, suppose I have a block, right, and if I have to draw a free body diagram, the first thing that I would do is like I will draw a force which is acting vertically downward, and this is weight, which is mass times gravity, and then there is a normal force which is against normal force which is perpendicular to this surface. And now there will be opposite force, a reaction force in this direction, which is W perpendicular. So which makes an angle theta. And now from this point, so there is a force which is acting on this direction, W parallel. Okay. So now what does this mean? So this force which is acting in this direction, this weight, this component of the force is responsible for this object to slide down the hill. And now what's the purpose of W perpendicular and W? And so because this weight is now acting in this y direction, but now because of this, now this component of this weight, so this weight is vertically downward. So this perpendicular component of the weight, which is counteracted and balanced by this normal force, what these two forces are doing it here. So this force, okay, it is sliding is down here. What these two force, what's the purpose of these two force? What these two forces does? Anyone?
Do they keep it on the ground or like on that
Ye-
surface?
Yes. The purpose of these two forces, they will keep this thing on the ground in this surface. If this normal force would have been larger than this perpendicular force of the weight, what happens? It will fly away. It will start flying away into up in the air, right? So this W perpendicular force and this normal force, which if they cancel each other, then this object will stay into the ground. That's good, Derek. Thank you. Okay. And this is a simple case when there's no friction. But now in the next topic, we're going to study about the friction, which is the opposing force. And if there's a friction between the surface and this object, so there's a friction force which is always towards the surface, always between the surface, parallel to the surface, and this is the direction of the friction force. The friction force will always be in opposite direction to the object. Okay. So now again for that purpose, I can show you guys another GeoGebra thing where you can again interact and play. it did not pop up. Okay. It used to pop up here. First angle. And in this one here, you can play with this one. So here in this diagram, I have drawn all this like a force component. There's a friction force and everything. So you can set the value of friction. This mu s and mu k, which is like a friction force. So when there's no friction force, and then I can change my angle, right? And then it will just stay on the ground, where this force due to gravity, this yeah, this force due to gravity cancel exactly to this normal. Now, if I will change this angle, right? If I move this angle, and as you can see, so it's moving. Like, let me put this some friction here so that it doesn't slide. I'll put in some friction. Oh my. Come on. Oh, it's not responding now. My touch is not responding. Okay, right? So as you can see here, so there's a force due to gravity, which is acting downwards, making an angle 24.2 degree with the perpendicular to this surface, right? This is the cos component, and this is my sine component. Because if I say this is my angle, so this is my cos component, this is my sine component. So again, it depends what angle did we use. So if you use this angle instead of this angle, if I use this angle, this is my parallel component, this is my perpendicular component. But here, this is like if I take this one, so this is my sine component. So generally, so now this angle of this slope will be, if this is my angle of the slope, now this is my angle of this force vector with respect to the normal. So this is all because of the geometry. Okay. So now this is my what? This is my right angle triangle, right? And then I can show you how does that thing work, because it's again important to know how those angles are there. So if I set this object here, and if I draw perpendicular here, right? So now what I know, this is 90 degree and this is 90 degree, right? So now if I say this is my angle theta, what is this angle? 90 degree minus theta. You guys following me? Yes. No. Yes. No. Maybe, right? So now this is my 90 degree minus theta. So that means what will be this my angle then? Theta. Yes. Because this whole angle is 90 degree. So this angle is minus theta degree. Right? And again here, because of this triangle, this is 90 minus theta. So this is my angle theta. Right? So now if this is my theta, again, so this is what component? This is my f g cos theta. And this is my f g sine theta. Make sense? So that means if we are given a numerical problem where we say that in the slope has an angle of say angle theta, so what is the force that is dragging the object downwards? Okay, so let me write down this. This g is looking like a multiplication. I'm just rewriting this one to make look like a subscript. Okay, make sense? Now you can also draw a free body diagram for the angle that is at an angle. So now I will copy this link to you in a chat so that you can go ahead and interact with this one and then see the force diagram and everything, right? So now, so the parallel component and so the perpendicular component, right? Oh my goodness, it's not again. Okay, it's not responding again. It's out of memory, maybe. Right. Okay. And where's my slide? So now the rule to draw a free body diagram, as I mentioned earlier, again and again, draw the body, subject of interest, as a point or a small block. So the immediate surrounding, that is other objects, body in contact with our subject, preferably in dotted line. Okay. And list out the various forces experienced by the object and disregard all the forces exerted by the body because they will appear as a force experienced by some other body in the system. Meaning if you have like two body of the system, you will draw a free body diagram for the two body independently. In the sense, suppose two bodies like colliding or something like that. And draw all the forces acting on a body as an arrows with the direction clearly marked, ignoring the force exerted by the body on others. Because the motion of body is solely determined by the forces acting on it. What does that mean? Is like in this condition, you are only drawing the forces that is acting on the body, not forces because of the body. Okay. Again, you have to draw like arrowhead, right? And label them parameters. And the way to draw this is called a free body diagram. Okay. And when we draw a free body diagram for multiple objects, then it will help us to navigate and calculate our forces easily. Okay. And that's like very important tool. Okay. So, so it's time exactly for about to be time for a break. And we will take a 15 minutes break so that you guys can go and eat something and then we'll come back and we'll continue more. Okay. Any questions before we leave? Okay, seems like no questions. See you at in 15 minutes. So 7:55. Hello all, welcome back. Are you guys back? Did I give you enough break time?
Yes.
Okay. Uh, okay, so let me see one thing. So Gabby, how are you feeling with the class? You're getting it, everything? So, let's see. Hmm. No, no. Okay. This one. So, Gabby, so can you show me your math with pre-calculus? Because in the one you have attached in the unofficial transcript, submit your unofficial transcript. So you have math 1314, which is college algebra. Yeah, can you
I'm
post
sorry,
me?
what you asking?
So I see your like in your unofficial transcript where you're submitting for the prerequisites, right? So I see only your college algebra. Do you have like pre-calculus?
Not college pre-calculus.
What do you mean? So what, do you have like any pre-calculus, trigonometries and all everything done before or no?
Yeah, I've taken pre-calculus before, but not in college. The math, algebra, whatever was the only college math class I took.
Okay. Hmm. Because you will have to take this pre-calculus, college pre-calculus courses. So where there is like trigonometry involved, right? So even if you take this course, like you have to go and that because your degree will be not complete because the prerequisites. So yeah, exactly. So that's why. So you need to meet the prerequisites for the class. So as I was saying that one, I didn't see that one in your unofficial transcript. I already gave a grade for like a 0, so that means incomplete because I didn't see it. So yeah, if you have anything, so where you have done like a pre-calc, then yes, you will be okay because you can take this course. But then again, as Dustin is saying, your graduation will be not complete. Your degree will not be complete.
Right.
Okay. Yeah, just letting you know. And I agree that there should be a better system where when you register for the classes, they should let you know. But I think like it will say the prerequisites there, but it will not stop you from the registering for the classes because you might be taking a course during this fall, right? And your class registration is in October 24th. So this course is not finished, but it has to let you register for physics 2 if somebody wants to do physics 2, right? So it cannot stop you from doing that one. So that's why you have to look at the prerequisites, and also it's always good to have a faculty advisor with you when you are registering for the courses, and that will help you make sure whatever you're doing it correct. Okay. So there's like a faculty advisor, and as I mentioned earlier, I'm also a faculty advisor, but I'm not allowed to give you any advising because you are my students right now. So I cannot give any advising. So I can only recommend you, you all, to not only to her, to everyone. Uh, so this website, go to this website and there's like a faculty advisor. So for science, engineering, and math faculty, you can get an appointment with any one of those people. Like there are 6, including me. So, okay. But I cannot advise you since you are my students right now. Okay. So just in case, and these are all free and you don't have to meet in person. It is like through online Zoom or like a Google Meet. Okay. So this for everyone. So like a free resource for everyone to decide what courses to take and what's the degree plan and everything. Okay. Okay. So being said that, let's go back to our thing. And yes, on Thursday, I will do numericals based on this one. Right now, what I'm trying to do is like I'm trying to give you a lots of concepts, understandings on these courses and what to expect. And then on Thursday, I will do numerical problems and then it will also help you for your test and also help you for your exam. Does that sound right? Make sense? You- Okay, I think like it sounds right to you all maybe. And the next topic is application of Newton's law. So where we're going to study about uh, different forces. Like as I said, as I have mentioned already in my Blackboard, if you go to my Blackboard in the syllabus sections, if you see the things that we'll be covering, all right? So, so we did this chapter 4. Now in chapter 5, we'll be talking about equilibrium of particles. Okay, let me share my screen. Mhm. Okay. Yeah. So in the syllabus, now there's now another topic that we are going to cover is chapter number 5, application of Newton's laws, equilibrium of particle, and this topic. And let me see, and exam. Okay, 6. Oh, okay. I am very behind. Okay. So we'll cover this one, okay? Now next topic that we're going to cover. And it is spinning. It is not loading in my iPad. Let me see. The chapter is not loading. Hold on a second. I will go ahead. Okay, finally it's opened up. Okay, good, good. Let me share my screen then. So the next topic, so like as we learned already, there's like so again, in Newton's law of motions, what we learned about the inertial frame of references, where the Newton's first law is valid, and what does the Newton's first law of motion also means is a law of inertia. So larger the mass, larger the inertia, or larger it will not try to change the state of rest or state of motion. Okay, and then we talked about how this force and acceleration is related. This force is related to acceleration with some constant factor called mass. And we also learned that in Newton's third law of motion, every action and reaction are equal and opposite. And also we learn to draw a free body diagram. And is that it about the force? No, of course not, right? And now, so again, in that conditions, there were no any friction force. So there is no any opposing force. There is no any drag. So what does that drag means? What does that friction means? So friction is when two objects are rubbing each other, then there's a force parallel to the surface in contact is known as a friction, and drag is something that pulls you behind, like for an example, a parachute. Of a person flying through the parachute, so there is a drag force that will let that person not accelerate at the very high speed and hit the ground and die or broke bones. So what does that do? So drag force will create a drag through the air and it will slow down. And similarly, we're going to talk about the elasticity. What's the elasticity? Elasticity is ability to maintain its uh, state of uh, art, or I mean to say like maintain its like original form. Okay. So now, before we do that, there's like a state of equilibrium, right? So what is this state of equilibrium is? So again, state of equilibrium is the conditions where the net force is zero, right? So net force is zero. So that means, again, so when the net force of an object is zero, it will be either in a rest or uniform motion, right? So that means, again, it's the same thing as a Newton's first law of motion. So the vector sum of all the forces acting on an object is equal to zero. Okay. So, and this also in a equilibrium. So now again, this state of equilibrium can be written mathematically as like F net equals to zero. All right. And like for an example here, a two-person pulling you with the equal amount of force, and this object is saying stationary here. So this is also a state of equilibrium, right? But what kind of equilibrium it is depends, right? So in these conditions, this force pulling on the x direction here and the force pulling on this x direction on this direction, they both cancel each other. And so the total sum of the forces on the x direction is zero. And there's like a gravitational force downward. And because of this tension again, so there is no force. So this upward force and the gravitational force, they cancel each other. All right. And now, since the net force is zero, what does that mean? Mass is not zero, but that means your acceleration is zero. So when acceleration is zero, what does that mean? That means the object could be at a rest or could be moving with a constant velocity, right? Remember the graph. Let me show you. Okay. If I would open this one, not the YouTube. Okay. All right. So in this case, as you see here, right? So this object is moving. And as you see, as this black dot is moving, you see this blue dot, which is the velocity plot. There's this one. This one is the velocity plot. This one is the position versus time plot. And this is the acceleration plot, right? So in these conditions, if I'm moving this black dot, my velocity is constant, positive, but moving with the same velocity, right? So which is about 5.9 meter per second. Now, what does that tell me about the slope of this velocity? My slope of this velocity is zero. So now if you look at this one, if we see this acceleration, what is it? It is zero. So that means even if my object is moving, right, and this black dot, this particle object is moving, it is moving with a constant velocity, all right? It is moving with a constant velocity, but my acceleration is zero. So this situation where my object is moving with a constant velocity is also a state of equilibrium, right? And the same thing here, if this object moves up and then comes down, so at this particular point, So it is moving with a constant velocity, right? Again, whenever the velocity is constant, my acceleration is 0. Whenever my velocity is not constant, right? For an example, here, my velocity is not constant. What is happening? My velocity is changing, right? At every point. So right now it's like this number, this 9.57 is the velocity. Sorry, there's a time. Velocity is like 1.3. This y-axis, 1.3 meter per second. So now as I am moving, my velocity is changing. So negative 2.9, negative 3, negative 47, negative 4.61, negative 4.99, negative 5.37, right? So velocity is changing. So that's why I have some magnitude of acceleration, which is not equal to 0. Now, as soon as I'm moving with a constant velocity, my acceleration is 0. So that's what I mean by state of equilibrium, right? So that's also net force is 0. It could be at the rest and it could be at a motion. So now in these conditions here, as we see, so there's like a triangular wedge and there's a beam which is staying stationary. So in this condition also, this is also a state of equilibrium. But what kind of equilibrium? Is it stable equilibrium? No, it's not a stable equilibrium. So, but only thing in these conditions, my net force is 0. So that means all the forces that is acting on the y-axis is balanced by this reaction force right at this point of contact between at this wedge at this center. So now what does that tell me? This whole beam mass is concentrated at this particular point. So that means that I can write down this whole diagram as a one dot point here, and with the force due to gravity, which is acting downward, and normal force is acting upward directions. And now here, this is also a state of equilibrium. So again, this equilibrium is different than this equilibrium. This equilibrium is much more stable than this equilibrium is stable, right? In this both case, force is 0. So now, I thought like I had that one. So that means if I have a ball and I have a marble, right? So now what happens? If I will swing this marble from left to right, so what happens? This marble will immediately try to fall down and try to be in these conditions, right? So this is the condition of stable equilibrium. And then another condition, I have this curve and I have this marble on top of this curve, right? And then if I will give a small push, then this will roll up and it will never come back up again. So this kind of equilibrium is called unstable equilibrium. This is a stable equilibrium. Make sense? And the next slide is about the friction, right? So once we know the equilibrium, the next topic is about the friction. What is the friction, right? So when the body is in motion, the frictions. So friction, is it important? So what we see, the friction is kind of like a negative force. Whatever the force we apply, it acts against our action, right? So that's the friction. So that means if I want to push something in an ice surface, it's so much smooth and nice, so easy to do that one. So now, does that mean the rough surface is a bad thing? I don't like it, right? Is that the thing? Basically, no. If there is no friction, then there is no way that we will be able to walk. Okay? Then there will be no way that we can walk if there is no friction on the object. And this friction is allows us to drive our car, walk. So like if you want to walk on ice, what happens? We're gonna fall down. there's no whether we can stand properly because there is no friction. So friction has an important role, right? And now this terminology of this friction keeps on changing depending on what kind of a medium you are in. If it's like a liquid and if it's then air, right? So there's a drag, all these forces, and then in a solid, it's called a friction force. Okay. So that's what I was talking about. So like driving a car and hitting a brake, we're able to stop. So if there's no friction, it'll keep on going. So that's why for that particular reason, in a winter season, we need to be very careful when we drive. If everyone here are from Texas only, but nowhere else, like if you go to Colorado during the winter season or like in Oregon or something like that, so they have a rule, or in Canada, so they have a rule like, winter tire, or like, you have to have like a chain to the tire. So why? So that will create an extra friction, because if there's an ice, so we will not be having a friction. So that creates a friction. So there's a traction. Okay. So and if there's no friction, it will just keep on going. You will not be able to stop. So this animation I try to create to make it a little bit of fun for you guys, but you guys are all good. So now there are two types of friction. One is called kinetic friction, and another is called static friction, right? So what does that mean? So by the name itself, right? So we did the kinematic equation of motions, right? What does that mean? Kinematic equation of motion. So kinematic means when the object is in motion. And static means when the object is not in motion, remaining stationary, right? So if the two surfaces are in contact and are moving related to one another, then the friction force between them is called kinetic friction, meaning if you're driving a car and once you hit the brake, your wheel locks and then the wheel will skid against the surface. At that moment, when it's like it's sliding, not rotating, when it's sliding, so in that conditions, it's called a kinetic friction. All right. Like for an example, if we have like these two blocks, one small block on top of like another big block. Now, if we push this block, right, and there's this friction force which is acting between this surface in contact. Like as we did earlier, so the force, we can push it with the hand, we can pull it with the string. So the force could be above the surface, right? Those applied force, the tension force and everything. But the friction force is the only one which is parallel to the surface uh, of motion, okay? And the friction force is always opposite to the direction of the motion, right? And this friction force, and mathematically, it is represented by a term f of small k. Okay. And what is this f? So this f of small k is equals to mu of k times n. So now what is this n? N is a normal force. And what is mu k? Mu k is the coefficient of kinetic friction. Okay. So now, larger the force of kinetic friction, larger the coefficient of kinetic friction, larger the amount of force. Now, if you look at this equation very carefully, all right, this friction force only depends on the coefficient of friction and the normal force. What is basically normal force means? What does it basically mean? On a flat surface?
It's the force that's perpendicular with respect to the surface that the object's sitting on.
Uh-huh, right. And in the flat surface, it is equal to the weight, right? Right. And now, does this new normal force is always equal to the weight? Is this normal force always equal to the weight?
No.
No, right? Yes. This normal force is not always equal to the earth force, because if we have, like earlier in example, what we did, right? So this angle here, so this normal is not equal to the weight, it is equal to the perpendicular, W perpendicular to the surface, right? Or based on this angle, we can also call this W parallel. So this we can also say like a W parallel because based on this angle theta, right? So it just depends. So this normal force is not always equal to the weight. Okay. So now, and then another thing to pay attention here is this friction force is equal to the coefficient of friction and normal. There is nothing else. Now, when I say a normal force of 10 Newton, what information do you get? What do you understand? Do you understand anything? Do you get any idea what I'm talking? Do you have an idea about the object? How does it look like? No, right? So we have no any information. So that means this friction force does not matter if it's a cylindrical, if it's a spherical, if it's like a rectangular, if it's a square, it does not matter. What it matters is what's the normal force against the ground. And it also does not matter what surface area is in contact with the surface. It's like a huge surface area is in contact, or it's just like a small section of the object. Like, if this something is like a circular or like, cylindrical, all right? Only the point of contact will be really small. So those point of contacts does not really matter for the friction force. What does it really matter is like, what's the normal force? Make sense? It does not depend on the geometry of an object. It only needs the what's the total normal force and what's the coefficient of friction. Okay. And similarly, for the static friction, again, in these conditions, when two surfaces are not in motion. So what does that mean? The two surfaces are in contact, but they are not moving, right? No matter if you are applying some force, it's not moving. And that is called static friction. And one interesting thing about this static friction is static friction will be zero if we're not applying any force. As we apply the static friction, as we apply the external force, there comes the static friction. Otherwise, there is no static friction. Meaning, the static friction is equals to the, again, the same formula, only with the subscript s, which is less than equals to mu s times n. Why this less than equals to? So maximum value of static friction that I can have is whatever the coefficient of friction, static friction. So this is a rough edge. Because of this rough edge, it creates a friction times the normal force. That is the maximum value of the static friction I can get. What do you mean by maximum force? Right? What does that mean is like, if I'm not applying any force onto this crate, if I'm not applying, so there is no any opposing force comes into play. If I will make this external force 0, my this opposing force, friction force, will be 0. So now if I will keep on applying this force, external force, my static friction force will keep on increasing. And it will increase until the point where it is equal to this maximum value, mu s times n. Right? And this is the Fs max, is the maximum amount of static friction. So what happens beyond this force? If I apply force beyond this value of this force, then only this crate will start moving. Any forces that is below this static friction force, this object will not move. It will stay there, stay put. Okay? And this maximum amount of static friction force is also known as a limiting static friction force. Like for an example here. Right? So now here, what do I have? You guys cannot see my pointer?
I can't see it.
Okay. So right. So now this person is pushing this car. This object is not moving. As you can see on this one, as I'm moving, right? Let me restart this one. Right. So what here you have this like a force. I can apply this force, and there's 50 kg of crate, and there's a like robot. AI is taking over. Okay, just making a joke here. Okay, so now if I am making a force towards the right, I need to apply the friction force that is between this crate and the surface. At this particular point, as you see the graph on this one as well, so there is no friction force. If this y-axis is my friction force and F is my applied force, right? This F is my applied force and F is my this. Basically, what you can say is like a static friction force is a response force. More you apply, more it responds. Less you apply, less it responds. If you don't apply, it does not respond. So that means it's zero, right? So now in these conditions, as you see, if I'm increasing my force, I'll keep on increasing my force. My static friction force will keep on increasing, and it will reach a point where it will hit the maximum, as you can see here, right? As I'm increasing this force, right? So my applied force in this direction and this friction force opposite in this direction, still it is not moving. Now it drops and now it starts moving. Now, what is my net force? My net force is whatever the applied force 262 Newton minus whatever this number is. What is this number? 103 Newton. All right. So that's the amount of force. And here's the net amount of force. Now, if we make a plot of this applied force versus friction force, this is how it looks like. And in this graph, from this point 0 to this point is the condition where the box is at rest. And this box is at rest due to what? The static friction. As you applied this force, my static friction kept on increasing, so my plot will look like this. And now, this point here, the box is moving. And here, and this condition is called a kinetic friction. Now, as you see here, this kinetic friction value, which is basically nothing mu naught times mu k times and this point here, starting point, is a static friction conditions where my applied force was 0, so that's why my static friction is also 0. And now this maximum peak point is the point with the limiting value of my friction force, where Fs is equals to max. So this is the conditions. This is the amount of force. If I apply any amount of force to an object which is initially at rest, this object will not move at all. Okay, so this object will be in a rest. But now, to make an object to move, we need to apply a force that is maximum than this limiting force. Then you say like, okay, now when the object is moving here, this force is much more smaller than this limiting amount of force. Yes, my kinetic force, friction force, is small than the limiting static friction force. Okay, once the body starts moving, my friction force decreases, and this kinetic friction force remains constant as it keeps on moving. Now, if you accelerate or if you go a little slower, it doesn't matter, it will stay constant. Okay, as you saw in this animation here. So like here, if I keep on increasing, now pay attention to this one, 30, 49, 59, 78, 99, and then 168, 173. And now here, all of a sudden, it decreased to like 133 Newton. So it's not changing. As I'm applying this force, this is not changing. This is constant at 133 Newton. So meaning, let me say this calculation because I cannot read that number clearly. 282 minus, yeah. So this is 133, right? So this, oh, okay, the mouse. Okay, I cannot see. Anyway, so now, huh? What happened to this? Sorry about that. My iPad just crashed. Okay. Right. So as you can see in these animations, so my friction forces are increasing, increasing, increasing. And then once it starts moving, it will decrease it to a value of 130 Newton, and more forces I'm applying, my kinetic friction force does not change. So that's what this graph represents. Make sense? So that means to make an object to move, we need to apply the force which is equals to Fs max. Unless we apply this force, the object will not move. And this region here, so that's why the static friction force is not a set value. It depends on the applied force. It's a response force. If the object is not moving, my friction force will be exactly equal to the applied force. Once my object starts moving, there is no static friction, there is a kinetic friction. And that kinetic friction force is is not a response force, it's a constant force, and it remains constant no matter if you apply the larger amount of force or like a medium amount of force, it doesn't matter. As long as it is moving, the kinetic friction force will be always constant. Make sense? Any questions there?
Why doesn't the kinetic friction, I guess, start at the FS max? Why does it have that drop and then go?
So it's like a breaking point, right? So once it break that point, then it will start moving. But once it start moving, right? And the the you know this as you saw, two surfaces, right? So
Yeah.
they will keep on opposing, right? At the beginning, it will very hard to make them move, but once it starts sliding, so this the edges are like bent, right? And then it is easy to go. But at the beginning, when it's like this locked in, they are locked in. But as you move, and once it breaks, then you don't need that large amount of force to move. Make sense? You are breaking that bond now already.
Gotcha.
All right. So there will be some like conceptual questions, some tricky questions. And again, when you are solving this numerical, and if these concepts are like really, really clear to you, all the problems will be like really easy for you to solve it. Okay. So that's why I'm spending time on these concepts. And also we'll do some problem on Thursday. So that's why this peak point is mu s times n, and this region is static friction force. And again, static friction force is a response force. Kinetic friction, okay. So these are the fact about like a friction force, which is always opposite to the direction of the motion applied. And this limiting force acts tangential to the contact surfaces, meaning parallel to the surfaces, okay? And the magnitude of limiting friction force is directly proportional to the normal reaction between the surface in contact, as I mentioned earlier. So it does not matter how what's the contact surface area. It does not matter on that one, okay? What's the geometry? Is it cylindrical? It's like a rectangular? It does not matter. What only it matters is the normal reaction, okay? And the magnitude of limiting force between two contact surfaces is independent of the shape or area of contact surfaces, provided the magnitude of normal reaction remains the same. So if my normal reaction is same, meaning if I have a 10 kilogram of like a metal in a cylindrical surface, cylindrical shape, and one in a rectangular shape, both of them are 10 kilogram, then the friction force created by those two objects will be same. It doesn't matter as long as they are of same weight. Okay. And this friction force, again, as I gave you an example, I say like a one metal, like, steel or something, both needs to be steel. If I'm taking like a different material, steel and a copper, then yes, they will be different. So that means this static friction force is the property of a material, right? So the wood will have a different friction force compared to a metal, right? And also, if I want to find the static friction coefficient, limiting friction force divided by normal reaction. Okay, so this will give me my maximum static. This will give me my static coefficient of static friction force. This is called coefficient of static friction force. So that was for the case of the object, like two objects in a contact. So now drag force is something which is with the air, right? So now let me see if I can share my sound from the computer. Computer sound, mono, whatever. And then if you see this one, so before I say anything about the drag force, I would like you to see this video, which is like very interesting to see.
Meet the superstar of the squirrel jumping game. When the southern flying squirrel takes off, his touchdowns are unrivaled. Biology professor Dr. John Scheibe has been captivated by flying squirrels for more than 20 years.
What we're going to do now is see just exactly how well this animal can perform, how well this animal can glide, what kind of distance he can get across our athletic field.
The squirrels launched in this stadium will fly, just as they do in the wild, at no risk to the animals. Their wings are flaps of skin stretched between their wrists and their ankles. Their hands and feet wiggle in opposite directions to help control their descent. A tail with feathered fur helps them change direction mid-flight. Cartilage alongside their wrists can slow them down for landing. This cartilage flares and acts like a stole tip on the wing of an airplane on a short runway. Kickoff hovers 50 feet in the air. Like the limbs of their trees, a branch serves as a runway. It's game time.
It's a tough starting point coming out of the back line from high atop the back of the end zone.
This is an absolutely perfect day to take a flying leap.
Well, it's a big time challenge before him. A lot of defenders, very limited options, but you know he's got a game plan. And there he goes. Let it fly. Look at that style. A picture-perfect glide hanging through the air. But wait a minute. He's hooking a right turn. Nobody expected this. He sticks the landing, goes under the fence and under the bleachers. We won't be seeing him back on the field anytime soon.
We have another 9 or 10 squirrels ready to go. These animals are clearly gliding, and they're actually doing better than just a regular glide. They're actually getting some pretty good distance. So I would say that they've done remarkably well. They have complete control. They can turn. They can even go 180 degrees. They can take off in one direction and land in the opposite direction. They're pretty spectacular.
Isn't that interesting? Yeah, I know. But then you have to also wear like this suit to follow this squirrel and then catch them. They can fly from that high, right? So yeah, when I saw this one, I was like, wow, this is like really interesting. So nature, right? So he's using the all like, physics, doing all the physics. And we need to do all this calculation to understand. They just do it, right? So now, what is this drag force? As you see in this video, the squirrel is opening up itself, like extending its surface area, right? So that means in these conditions, remember in the friction force, the area is not of any concern. But in the case of a drag force, larger the surface area, larger the drag. So meaning you are collecting the larger amount of air, right? So that means it will slow you down. So if any one of you are swimmer, so if you want to swim, you want to make the body streamlined, but not at an angle, right? What happens if you make your body at an angle? Again, there's a drag force. It's the same reason. So it will slow you down. But for the squirrel jumping that high, it wants to slow down. Slow down against what? Slow down against the acceleration due to gravity, because if it does not spread its wings, otherwise it will fall at the speed of 9.8 meter per second square increase in velocity at every second, right? So now to slow down that rate of increase of velocity, so it is using its wings to make that acceleration due to gravity, change in velocity a slower rate, or with the velocity something terminal velocity. And the force that is helping to slow down its motion is known as a drag force. So this drag force is opposite to the direction of the motion, like similarly as in case of a friction force is opposite to the direction of motion, the drag force is also opposite to the motion, and but is directly proportional to the square of the speed of the body, speed of a body. So how fast is moving? Higher the speed, higher the drag force. Okay. And it also depends in the cross-section area of the object. If the larger is the cross-section area, larger is the drag force. To create a larger drag force, you need to have a larger surface area. So like for an example, like for a parachute, right? If there's like some parachute like that you can buy, so like generally the athletes use it and during their training. So what they do is like they tie their parachute on their back and they run. And when they run, what it does, the parachute opens up and then it will collect an air and it will just make you go slow, right? So, um, okay, here, so this is what I was trying to show you. Then this one, copy image. So hard to paste, I don't know why. Paste. Okay. Pasting. Okay. Yeah, this is what I was talking about. So now, to get this drag effect, you need to run really, really fast on this one. That's why if you don't run, what happens? This parachute will fall down and you don't get a drag, right? So to get this drag, so that means you need to run faster. So that means V needs to, so this drag force is directly proportional to how fast you're moving. And then also depends how big this parachute opens up. And another training in a they do is like in a swimming. So what they do is like there's a swimming parachute, right? So they do as they as they are swimming. So this faster and faster. So it will collect more and more water, and it will drag you more and more backward. Okay. So faster you move, the uh, the more the drag force would be. Okay. So that's what I mean here. This FD, which is directly proportional to the cross-section area and the speed. And it is proportional to the density of the medium, meaning, so like as I gave you an example of like in air or in a water, right? So if the density is like higher, higher is the drag force. So like, for example, if you drop an object in a maple syrup, and if you drop same object in a water, like a metal ball bearing in a maple syrup, and if you drop same ball bearing in a water, it will travel slower in a maple syrup compared to the water. Why? The density of this maple syrup is much more higher, right? So that means the drag force, the opposing force is much more higher. So that means the drag force is larger for the density. So that means density plays a direct role in terms of a drag force. Okay. So and hence mathematically, it is written as Fd is equals to 1/2 C, which is a constant, the density, area of the cross section, and this velocity square. Okay. So this constant of 1/2 C is a constant factor for this drag force. Okay. And this C is nothing but a dimensionless empirical quantity known as a drag coefficient. Okay. Larger the drag coefficient, larger the drag force, same as mu. So now for this value of C, for depending upon it just depends on the geometry, right? Even in geometry of an object. So like a different car, like when they build, so they have like different coefficients. So larger the coefficient, larger the drag force. Now, if you want to build a like very high fuel efficient car, what do you want to do, right? You want to reduce the cross section area, and you want to have the C value much more smaller, right? And density, you don't have a control. It's the density of the air. V is the like speed, higher the speed. So that means you want to reduce down the cross section area, and you have like a build a design in such a way that your drag coefficient C is smaller. So now here is like different comparison of like different objects. Here, airfoil, which has a drag coefficient of 0.05, and Toyota Camry has a 0.28. And here, as you see, the highest number of drag circular flat plate has a higher drag uh, coefficient, and the skydiver 1.0. Definitely, yes, we want like a higher drag force or drag coefficient for a skydiver. If there is a very small amount of drag force, then what happens? Oh my goodness, the person gonna hit the ground really, really hard. So why this is all important? And we already know in our freeway, not in Texas though. So if you go out of the states, like, or we can say the frontage road and all those things, like, in Texas, not the freeway. So there are like a speed limit of 55. If you go to Ohio, in a freeway, the speed limit is 55. Trust me, it's so slow after being here in Texas. I lived in Ohio for like 7 years. Now I see like 55, the speed limit of a freeway. Oh my goodness, when am I gonna go from one end to another end? That's what I feel now. So, but now again, so this speed limit of 55 is mostly common in most of the states in a freeway. Some of them had like say 60, 65 and other things. And there's a reason for that one. And the reason for that one is a drag force. How this drag force is playing a role, right? Earlier, when they made a car, right? Over 50% of the power of the car is used to overcome the drag force, right? And the most fuel efficient cruising speed is about 70 to 80 kilometer per hour, which is about 45 to 50 miles per an hour. So just to make this car fuel efficient, right? And have like a maximum efficiency. So the speed limit was changed to 55. For this reason, in 1970s, during the oil crisis in the United States, maximum speed on highways were set to 90 kilometer per hour or 55 miles per hour. And this for the energy purpose, right? So this 55. So it's not like some magic number, say like 55, right? If you go to like Canada, the speed limit in freeway is 80 kilometer per hour, which is 50 miles per hour. And trust me, if you are so much used to of driving here, and if you go to Canada, as soon as you cross the border, you will be so confused. I was so confused. I don't know about you guys when I saw like, going like 35 miles per hour at the border area, and then as soon as I cross, and it's like a 25 kilometer per hour, and it's like, what is this 25 kilometer per? I know this number, but what is this 25 kilometer? What is the speed? And I was like having a so hard time, and it was like about 15 uh, miles per hour about, and like, oh my goodness, right? So this unit conversion always tricks you as well. And also, and that's the reason for the drag force. The most of the freeways are about like 55 miles per hour to make it fuel efficient. Make sense? Something history associated with the physics. Okay. So based on the physics to make your efficient, get the most out of your car, right? So that's why like in a freeway, if you're driving 90 miles per hour, your car says like not efficient. It's not because of only the engine running harder. It's only because it has to work against the drag force. So because that's what we saw, higher the speed, V, higher is the drag force, right? So in this expression we already saw, right? So the cross-section area, we can do nothing about the cross-section area density, very much less control, because either it's humid or it's rainy or it's like a dry day. So like rho is constant. So C is some constant. Only thing that you have in your control is like V, right? If you go a higher speed, higher drag force. So that's why uh, the efficiency speed is about like 55 miles per hour. And that's why your car shows like green at that particular speed. And the terminal velocity is the velocity, is the condition of the velocity where the net force is zero. The net force is zero. What does that mean? If an object is dropping down, the force due to gravity, which is acting downward, and the drag force, which is acting opposite direction, if they are equal, now since the object was already moving down, it will keep on moving down with a constant speed, constant velocity. And that conditions is known as a terminal velocity. So terminal velocity means the object will move with a constant velocity down. And that's the condition of a Newton's first law of motion, where An object in a state of motion will continue in a motion unless acted upon by a uniform motion in a straight line unless acted upon by an external force. So that means this object thermal velocity is the conditions when the normal force and the gravitational force, they equal. So in this here, the normal force is a drag force if it is dropping down to the parachute from the air, from the airplane. Okay. And mathematically, so what we know, so force due to gravity. So if there's an object, force. So here, the force due to gravity is acting downwards, and this force due to gravity, and there's a drag force which is acting down upward, right? So now, if this force due to gravity, which is equals to nothing but mass times gravity, and this drag force is nothing 1/2 c rho a square, right? So now, if these two quantities are equal, then my net force is 0, and that's what it's doing here. mg is this force due to gravity, which is acting downward, and Fd, which is the drag force. If they are equal and opposite, then my net force F net will be 0. So what does that mean? And at that particular conditions, my drag force will be equal to the weight of my body, weight of the object of a body, right? And what we know, drag force is 1/2 c rho av squared equals mg. So that means from this expression, I can calculate my terminal velocity. If I know what is the mass of an object, if I know what's the density, if in air, we'll use the air density. And if I know my object and what is this like a drag coefficient, C, if I know area of cross section, then I can calculate what will be my terminal velocity. Okay. Makes sense? So that I can maintain my speed. So this is another example here. So which I was trying to show you here about the terminal velocity. So what I have here, I have like
Here,
4 tubes,
I have a
right?
different
So
size
4
of
tubes, and this
ping pong
tube
ball.
size is like a
This is
size of the
smaller
ball,
in cross-section
or
area.
tennis
This is a
ping pong ball.
little larger
This
in
ping pong
cross-section
ball
area.
is a little bit bigger
And this one.
than this
And here this is a
on a small ball.
funnel pong. So the cross-section area of this is like of this same size of this ball, not this one. So this will feel a more air drag compared to this one.
Right. So now the cross-section area. So now in this condition, the cross-section area is larger, and also like there's like less escaping of the air. So that's why it was flowing with a slower speed compared to this one, which has a smaller cross-section area. So that means the drag force is smaller to this one compared to these other objects, right? Make sense? Are you guys following me? Right. So, and I'm involving like a little bit less math here, but again, we'll do problems on Thursday. And elasticity. What do you all understand by saying the term elasticity? Do you guys have any idea? So like, what does this word mean by itself? If you have not heard about it, anything, what you guys can say about elasticity, or what does it mean to you when you say elasticity? When you say something is elastic, what does it mean to you? The ability of an object to maintain its form. Yes. Okay. Anyone else? Okay. So now if I say I have a steel, a rod of steel, and I have a rubber band. Which one is more elastic? Derek is saying rubber band. Anyone? No one? Okay. So what do you think, Dustin? Which one is more elastic, rubber band or a steel rod?
I would think the rubber band is more elastic.
Okay. So that means both of you are wrong.
Oh, really?
Yeah. So as you said the definition, the ability of an object to maintain its form, right? So yes. What does that mean? The ability of an object to maintain its form. So that means if you apply a force, it will not change its form. It will not give up its form easily, right? So that means for a steel rod, if you want to stretch, how much force you need to apply?
A lot.
A lot. Compared to the rubber band, how much force you need to apply,
Very little.
right? For the band, very little. So that means with that little amount of force, you can change its form, right? So that and for the steel, with the same amount of force you apply, it does not change, right? So that means the steel has more ability to maintain its form than the rubber band. Hence, steel is more elastic than rubber band. Yes, rubber band is more stretchy. It's more stretchy than steel. But elastic-wise, by the definition of elasticity, the steel has more elasticity. So that means it does not give up its form easily. So you have to apply a huge amount of force.
So to call a pair of pants that has an elastic waist.
Sorry?
So when they say that if you have like a pair of pants and they have an elastic waist, it's actually less elastic if it's more stretchy.
Yeah, so I didn't understand your first term. What you were saying, like the elastic waist, what do you mean by
You know how like some pants they make waists that are stretchy and they call them an elastic waist.
yeah.
So does
So
that
yeah,
mean that it's actually less elastic?
yeah, it means it's stretchy,
Yeah.
right? Right, but not exactly elastic. So the definition of this elasticity, elastic means. Makes sense,
Yeah.
right? So gold can be more elastic than, no, gold is like more like a is more easily malleable and ductile, right? If you take a pure gold, 24 karat gold, right? So that is easily bendable than the steel. So steel is not a pure metal. It's an alloy of iron, aluminum, and some other like impurities. And that composition makes it like more stronger. And now comparing, so now think it this way. So when we say a steel rod, so we think about like a very big fat rod, right? Now if you think like a web, like a spider web, and you know the spider web is much more elastic than the steel spider web, right? So now when you make a steel of like that very thin, yeah, it will be same thing like a stretchy. It will stretch, it will not break, but the spider web is even more stronger than the steel. So now when you see the string, spider web, very thin one, you can stretch it, right? There will be some stretching, but it will come back to its original position. Now the elastic band, that the rubber band that we have, if you take a strand, like, so if you make like very thick rubber, that will also be like a, what do you call that? That will also very strong, right? But when you are talking about like a elastic band in your like a pants, yeah, as little, how do I say it? So there is also like a small like little bit of fiber, they are attached together. I don't know. How do I say that one?
Well, so I
You
guess
got
it's
the point.
not about whether it's stretchy, right? It's about whether or not it returns back to its original form
Yes.
after being stretched.
Yes, right? It's a response, right, to the like external force. More you apply the force, then only you can change its shape. It will not, otherwise it will not change its shape. So how well it can maintain its form.
Okay.
And now based on that one, so now if I take a steel and I make it in a circular loops, and then I attach an object, so now the same steel can be stretchy, right? And now, so what happens? So now for an example of this spring, sorry, in the spring, so if I put this mass and if I pull back down, so it will try to go back to its original position immediately, right? If I pull this thing down, what happens? It will get stretched. But now because it has a tendency to maintain its original form, so there will be a force acting in opposite direction to the direction of force that we apply, right? And now this is called a restoring force. This restoring force that is in response to the force that we apply. So this force is not something that we supplied. This is a response from to the our force. So that means as soon as we let it go, so this force will pull this object back into the original position. But now when it does that, it always overshoots a little bit, right? And then it compresses the spring, and then again the spring does not like it, and then it will now spring will push forward to go back to the equilibrium position. Again, it will overshoot and then go back, and it keep on swinging. Now, if this is a perfect ideal conditions where there is no damping. So damping means where there is no any uh, uh, opposing force that will oppose these oscillations, like moving back and forth. So damping force, that is a restricting force. That's opposing force. That's a resistance force. So if that damping force is not present, so now once I give this initial force, it will keep on oscillating back and forth at this equilibrium position. Now, as you see here, so this is my equilibrium position. Now, what does this look like? This is my equilibrium. And so that means from this, my equilibrium, my object is moving up and down. Now, as you see here, what is this? So simple up and down motion is what? A nice wave like a motion, a sine wave motion, or a sine cosine wave function, right? So when I pull it up, so it goes up and down, right? At the equilibrium, equally down, equally up in ideal situations, right? And for an example, I have here this straight the spring and then let it go. It oscillates. Okay. Okay. Because it was responding slow because I was not able to show you the video. I'm redoing it again. One more time. Here. And there's a spring. If I take the spring and I let it go. So this motion is simply up and down motion. But now if we trace this motion with respect to time, we will see a very nice sinusoidal wave motion. And then same thing here. So elasticity, if I pull this string out, if I release it, it will go back to its original form, all right? So now here this steel is also stretchy. Right? So now, according to Hooke's law, right? So if we pull an object, so what happens? So there's a restoring force. So that means this restoring force is proportional to the amount of the force that we apply to displace it. So now in this particular case, so suppose this is my equilibrium position, right? So in this equilibrium position where I'm not applying any force, which is 0 Newton, and my displacement is also 0, right? And now, so if I look at my plot, this displacement over applied force, my displacement is 0 since my applied force is 0. So right now we are at this particular point. So now as we clamp it and then pull, so this increases and we push, this goes down here, right? So now what is this? This x-axis is a displacement. This is y-axis is my force. Now as you see in this one, as I am pulling, there's an energy, sorry, there's a force displacement and there's a force, right? So that means it is moving in these directions. So applied force is positive. If I say this is my positive displacement, this is positive. Now if I push it, my applied force is negative, my displacement negative, or in the sense that suppose the spring is pulling by itself. So that means if I, let me see if I can open up the FET simulation. Let me, I can do more nicely here. And then there's no Hooke's law. Working is in power. Come on. Okay. Applied force is spring. And where's the graph? But they got rid of the graph? Oh, here it is. Okay. Right? So not the inertia. Force plot. Displacement. Okay. Equivalent position values. Okay. So now in this one, right, I'm applying a force. Right? So now I applied a force of 40 Newton. Right? I applied a force of 40 Newton. I like 100 Newton here right now. And I displaced by a distance of 1 meter. So 1 meter is the displacement. 10 Newton is my force. So now it is going into this direction. So now this is following a very straight line. So now as I will now let it go and then push it here. So what do I have here? So this my displacement is negative displacement and force is also negative, right? The applied force is negative. Okay, and based on the spring constant. So now if I will take this ratio of this rise over run. So 70 divided by 0.7, what do I get? I will get 100. And what that 100 is? That 100 is the slope of this force against displacement plot. Make sense? And that slope, 100 is what? The spring constant. So that means by what force it will be pulling backward. So this is based on the slope. So now if I will increase the slope of my spring, right? So that means I have to apply large amount of force to move the same displacement. Now, if I will reduce my spring constant, so that means I need to apply small amount of force to move the same displacement. Now, if I move my another displacement here, my force keeps on increasing. And this force versus displacement plot gives me a straight line, a linear line. And the slope of this line tells me what is my spring constant. So that means it tells me the ratio of force and displacement. How much force I need to apply to achieve how much of my displacement. Make sense? Make sense? So now this is the conditions where this spring is still maintaining its position, right? So now here the spring is able to maintain its position and go back and forth, right? But now in a real situation, if we keep on stretching our spring, we will break it as well, right? So now, but before we move into that point conditions, in this situation where my object is able to get back to its equilibrium conditions, so now in that condition, in this condition of spring, this f of spring is equals to k times delta L. What is k? K is a spring constant. That is the slope of this line. And this delta L is what? The displacement. Because as we saw, larger the displacement, larger is the force, applied force, right? And that is based on this spring constant K. Larger the spring constant, larger the amount of force we need to create a same displacement. Okay? And this K is known as spring constant. And if I am applying a force in this direction, my force, the restoring force, I would say right now, the force due to spring is always towards this equilibrium. So now if I will, in this condition, if I'm pulling this one, so my restoring force is always towards the equilibrium. My restoring force will be from this point, it will be directing in this direction. Okay. While my applied force is from this point is applied to the right, my restoring force will be from this point towards the left, towards the equilibrium. But now when I will push, my applied force is at left direction from the equilibrium. From here, it is to the left, but my restoring force, the force due to spring, will be again opposite to this applied force, which is again at the direction of what? To the equilibrium. So because this is my equilibrium, this force due to spring will always towards the equilibrium. So meaning if I pull this, even if I pull a small distance here, my applied force is in this direction, my force to the spring will be again towards the equilibrium at this particular point. Okay? Make sense? Make sense? And now, the reason that we were doing earlier right now, so this was the reason, is the reason where the Hooke's law is obeyed. So as we stretch this, there's a restoring force. This restoring force will be equal to the spring constant K times the displacement. But and then this region is still our elastic region. And if we further go beyond that point, so we will have a deformation in the shape, but still it will have some property of going back to its original position, but it might not go completely to the original position, but somewhat. Like, if you stretch the spring too much, so it will stretch and it will lose this property. So going back to the real original position. So that's what it happens in this region if you go beyond this Hooke's law region. And then if you go beyond this elastic region, then there's a permanent deformation of an object. And even if we apply the, even if we keep on applying this force, then at this point where there is a fracture, where we'll snap the object, will break the object. Okay, and this is a different reason of the force that we can apply. Okay. Force, elastic forces. Content. Now, what are they? Okay. Component forces. Okay. What are is there anything left? Elastic forces. Yeah. Forces. Any questions until now? Do you guys have any questions? So things are like little clear, right? Understanding. Okay, let me see a problem so that I can do a problem with you guys. Okay. Okay. Okay, copy, and I'll go back here. Do you guys have any questions before we move forward? Nothing, no questions. Everything clear. You guys are understanding, able to follow me, even though I'm going with like so many things. Okay. So now let's see this problem. Suppose that a delivery company had just unloaded 500 Newton crate full of home exercise equipments in your level driveway. So level driveway, so it's like a flat. You find that to get it started moving towards your garage, you have to pull with a horizontal force of magnitude 230 Newton. Once the crate breaks loose and it starts to move, you can keep it moving at a constant velocity with only 200 Newton of force. What are the coefficient of static and kinetic friction? Okay. You guys following me? Yeah. All right. So that means the first again, when you solve a problem in your exam, right? I want you to follow these 5 steps. Number 1, write down the uh, parameters given, and then write down in correct unit, which is basically SI unit system. Okay. And then write down what needs to be calculated. Okay. And then 4, draw free body diagram. 5, write down the equation. that you are going to use, and sixth number is like your solution, right? And make sure your final answer is boxed with correct unit. Okay, so there are 6 steps to follow. Whenever possible, if in the problem needs a free body diagram, draw this free body diagram whenever possible. Okay, so like for in this problem, all right, so one of the requirements, so like everything that we are given here, what we are given here is solution. So given, so a car unloaded 500 full of exercise equipments, right? So mass M1 is 500 Newton. So not the mass, weight, right? So this is like a 500 Newton. And the force that you need to apply, applied force, is 230 Newton, right? So this is what maximum, right? And now once it kinetic friction force, Fk, is now 200 Newton force. Now it is asking what is mu s, what is mu k. Make sense? Now it is asking what is my mu s, what is mu k. Now let's draw the situation of the case. I have this surface. I have this block. Oh my goodness. Let me do this. It used to make this. Come on, make it rectangle. Didn't make it. Yes. Right. So I have this box now, which is about 500 Newton. And now what I have to do, according to the problem, I have to pull with a force of 230 Newton, horizontal force. So that means I am pulling with the horizontal force of like 230 Newton on this direction, right? And this is 500 Newton is my weight of this object. So that means this 500 Newton is acting downwards, right? And then there is my normal force, which is upward, which is my normal force. And then there is my friction force, which is in opposite direction, Fs max, right? So if I'm applying a 230 Newton force, so this is my maximum amount of force that I can apply for this object to move. After this 230 Newton, it will break loose. It will break loose, and then it will start moving. The crate will break loose and it will start moving, right? So that's my question is. So now I need to find what is my mu s. So using these conditions, I can find my mu s. I can find my mu s. This is condition number A, right? So now let's solve for the condition number A first. And also don't write your things everywhere. So it will, if you write it down vertically rather than writing everywhere, so that it will be easy for me to what do you call that? Grade your homework as well, or like a grade your exam, right? So now what we know is normal is equals to 500 Newton, and from this definition of Fs max is equals to mu s times n, right? So what is my Fs max? Fs max is equals to applied force is equals to 230 Newton. So that means mu s is equals to Fs max over normal. So this is equals to 230 Newton divided by 500 Newton. So 23 over 50, which is around like, so 23 over 50, just less than half, 0.46. So this is my static friction coefficient. Again, static friction coefficient has no units because this Newton and Newton cancel each other as well. Okay. Now for part B. Okay. And for part B, again, what we know, my object starts moving. Come on. It goes in other direction only. Oh, you have to go to the right direction. Clockwise, then only it makes object. Okay. So I have my surface. And then in these conditions, I have my force, kinetic force. Fk is 200 Newton. And my friction coefficient force, Fk is mu k times n. And here I have my 500 Newton. And then here I have my normal, which is equals to 500 Newton. Right? So now what we know, it's very simple. Fk is mu k times n, which is equals to F applied, which is 200 Newton. So that means mu k is equals to 200 Newton over 500 Newton. And this is equals to 0.4 Newton. So now what does this tell me is my kinetic friction coefficient cannot be larger than my static friction coefficient. My kinetic friction coefficient is always smaller than the static friction coefficient. Okay, so that's why I have in my here, as you see in this one, what should be, so now what you can do, right? So this one was by very simple problem. It was in a flat plane. So now what you can do, so if I have this in a inclined plane, right? If I have this object in an inclined plane, so with certain angle theta, so what should be my value of mu s or mu k so that the object will just start sliding down, right? So what should be my mu s and mu k? So first, given mass of an object, or given mass of an object. So what you need to do? So in this condition, you need to draw a free body diagram, which is downward, this normal, and this force here, right? So this now, without applying any force. Now here, what we are doing it here, we are not applying any force. We are using the force due to gravity, the component of the force that is acting downward here. So now this is W, which is mg, and this is theta. What is this component? mg cos theta, and this is mg sine theta, right? So in these conditions, my normal, in this condition, my normal will be equals to what? Mg cos theta, right? So that means my friction force in these conditions, SF max, would be what? Mu S times N. What is my mu S? Mu S is mu S. What is my N? Mg cos theta. Right? So you can also get like static friction coefficient using this one. And also when it starts sliding, so what's the amount of force acting in here, right? And acting in there, right? And now, so what force is letting it go sliding down? So we know this force maximum here. What is this force? So this force must be equal to this force. And then how we will calculate, because now in this problem, we will given this theta, or we can calculate theta. If we need to find theta, we can calculate theta. And then this should be mg sine theta must be equals to mu s mg cos theta, right? So that means in this condition, what happens? mg cancels. So that means my mu s is standard. Okay. So now in this one, so go to this GeoGebra. So I'm not giving you a homework, but I'm giving you a tool where you can verify yourself. Okay. So you can change the mass, right? If you change this mass, you can see this arrow increases and decreases, and where you can change the value of mu k. So, and remember, again, it froze. And remember, this mu k cannot be greater than mu s. Okay. That's why here, so mu s is 0.136, mu k is 0.128. That's the maximum value it can go, right? If you keep on getting your mu s larger, so as you can see here, this f in a red color is getting larger. Okay. So may S, and now to make this angle slide, so what should be my angle so that it will start sliding? So that means I can change my angle of inclination. Then at this particular angle, it will start sliding, right? And then you'll see this one. What if I decrease and then it stops? This angle, it stops 36.2. If you increase just a little bit by 2, at 37, it is increasing. 37.2, yes, increasing. And also it is giving you what is the maximum velocity it will gain when it reaches the bottom. When this blocks reaches the bottom, what's my maximum velocity? As you can see here. It is so what is the maximum velocity and how long it takes time, and as the velocity is increasing, and what is my acceleration, what is my normal value, so what is the force down the ramp, what is the friction coefficient, and what's my kinetic friction. But here my kinetic friction is 0 because mu k is 0. Now if I increase my mu k, then you can see my friction coefficient is also increasing. Now if I increase more friction coefficient, now it's moving slower, 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 and slower, right? So I can control all these things, and you can see what's the maximum speed I can go down the hill, what will be my velocity and how long it takes. It will show you the time and all these things. Okay. And if you like this friction force to show onto the surface, but not in here, to make it exactly sure what the friction force is, you can do that one. You can select this different tool. Okay. And if you like to draw a free body diagram, and if you want to learn, again, you can always hide these forces and then draw the free body diagram by yourself and then see if it matches to this one. Okay. Make sense? And here itself, you can create a multiple problem and then solve it. Make sense? Okay, so let me give you guys the link for this site. Or did I give you already? Oh, okay. Everyone. Oh, did you do it like Ernest today? Jacob. Okay. You are present today, Jacob. Today you are present. For the earlier day, you said like past. Show me a proof where you were in the class. Yeah, so that's what I'm saying. Like, show me, like, oh, that you're in a class. So go to the video and show me the interactions, like in a recorded video, and then you can show me, and then I can give you the credit for that one. Okay. So in a recorded video, you might have interacted. Show me the timeline, and then I'll go in and check, and I'll give you that one. Louis is not here today. Okay. Any questions? Okay, so we are until what time today? Again, I have to go back to syllabus. No, not syllabus, start here. Okay. So now a very small topic remained, which is like a uniform circular motion. And we will do that on Thursday. And we'll also do some problems and revisions. So like as we did, right? And then I'll leave you guys for the test. And I'll also post the homework, but the homework will not be due until the final is midterm is done. Okay. So, but look at the homework problems, which will also help you for your midterm. Okay. Do you have any questions before we leave today? Okay, looks like there's no questions. Okay, and I'll say a good night to everyone. Bye-bye.